Okay, welcome back. This is Calc 1, the last section in Chapter 4, and it's about differentials. And we'll begin with this idea of a tangent line approximation. Okay, so step 1, the tangent line approximation. Okay, so you have some sort of function doing what it does. Okay? And what you're going to do is kind of use a tangent line to approximate the function in a given region. Okay? So if you were to zoom in maybe on a box in this region here, it would seem, okay, so kind of expand this box, it would seem that the curve and the tangent line are kind of close together, right? So the tangent line, I'll put it right here. And if you kept on zooming in, the actual curve would almost seem flat. So it would seem like a really good approximation to the curve eventually, okay? So that's kind of the heart of the idea. We are approximating a function around a particular point with a tangent line. So to get the equation of that tangent line, I need a point and a slope. So I can get this point as c comma f of c. And then the slope of that tangent line is given by the derivative, right? So I need, for the tangent line, I need this point, c comma f of c, and then I need a slope. So the slope will be the derivative of the function evaluated at c. Then we just go to our point slope form, y minus y1 equals m times x minus x1, and substitute in our values. So we have y minus f of c equals f prime of c times x minus c. And then we'll move the f of c over. And this will be our tangent line approximation, which sometimes they call t of x. Okay? So you'll have f of c plus f prime of c times x minus c. And if you take Calc 2, you'll look at polynomial approximations. And eventually this will lead to Maclaurin polynomials and Taylor polynomials, and then Taylor series and Maclaurin series, all that great stuff. Okay, so this equation right here is the linear approximation of f at c. Okay, so an example, maybe something like use the linear approximation and compare the values of the actual function and the linear approximation. Okay, so use linear approximation. Basically, in the homework they'll give you like a chart you have to fill out. So, anyways, the function we'll look at is e to the x, and we'll worry about a c value of 0. Okay, so for our formula, we need what? We need f prime of x, which is again e to the x, and then t of x. This linear approximation will be f of c, so f of 0 plus f prime of 0 times x minus 0. And so f of 0, if you plug 0 into e to the x, it'll be e to the 0, which is 1, plus f prime of 0 will also be 1. And then x minus 0 is just x. So this linear approximation is 1 plus x. Okay, if you were to draw it, the exponential growth function looks like this, and then 1 plus x will be a line right there. Now, we want to compare the values of f of x and t of x around 0. Okay, so we'll have f of x and t of x, and we'll make a chart. So, I don't know, 0.1, and then we'll get closer to 0, 0.01, 0.001. We'll just do 3 values. Okay. So I'll plug this into e to the x. So e to the 0.1 equals 1.105, and then 0.01 will give you 1.010, and then 0.001 I'm doing this in my calculator, that's why will be 1.001-ish. These are all approximations to 3 decimals. If you put it into t of x then, and t of x from above there is this guy. If you plug things into there, you'll get 1 plus 0.1 is 1.1. Then 1 plus 0.01 is 1.01. And then 1 plus 0.001 is 1.001. And you can see that they're pretty close, but the approximations get worse as you get farther away from that center. Okay, so great. We can use equations of lines to do approximations and areas. This is great because equations of lines are what we're used to. It's what we grew up working with. You'd rather work with equations of lines than some weird transcendental animal that is confusing, right? Okay, so there's that. Differentials. So moving on, differentials. Basically, a differential is the top part of your derivative. So you have change in y over change in x. We're interested just in the change in y as we go from x to x. Okay, so a differential is the approximate, or the approximated change in height, which is delta y. Okay, okie dokie. So let's take a function of some sort. Maybe it's some sort of U-shaped type deal. I probably didn't do my graph justice. Let's try that again. Now it's just erasing everything. And okay, so let's try it again. So some sort of U-shaped curve. Maybe it goes off like that. What we want to do is compare the change in height of the tangent line to the change in height of the actual graph. Okay, going from some point C to some point C plus change in x. Okay. So the actual change in height of the function, okay, in this case I've gotten carried away with my graphs, so it's going to be quite big. So this point maybe is way up here now. The actual change in height of the graph from C to C plus change in x is called change in y. Okay. The differential is going to be then the change in height of the tangent line. Okay, and that'll be little dy, which should be like the top of your derivative. Okay, so let me maybe use a different color. So the change in height going from that bottom red line to the upper blue line, that's going to be our little dy. Okay. And what we're saying is when this change in x is small enough, that little dy and the delta y will be approximately the same. Okay. So some definitions before we get too carried away. Delta x, which is also going to be the same as little dx, is the differential of x. Delta y, which is, let me erase that, sorry. Little dy is the differential of y. Okay, so little dy which we'll find is equal to f prime of x times dx, or delta x if you'd rather, is the differential of y. And also then, as change in x gets really, really small, we can approximate the actual change in y with the differential of y, okay? Which of course then is equal to f prime of x dx. Okay, so algebraically speaking, with symbols and stuff like that, what is this delta y? The delta y is the difference between f of x, or rather f of c plus change in x, and f of x. Okay, it's just a difference in heights. The dy is the difference in height between the tangent line approximation evaluated at c plus change in x, and this should be above, it should be an f of c. So this should be f of c. And again, f of c, it's those two heights. And you could evaluate the t of c plus change in x. If you remember, just to the side on the upper left here, t of x was equal to f of c plus f prime of c times x minus c. Okay? So if we plug c plus change in x in for x, wherever we see x, we get f of c plus f prime of c times c plus change in x minus c. Sorry, I'm having to smush that in. And then minus f of c. And of course, you know, the f of c minus f of c is 0. And then you get f prime of c times c minus c is 0, so change in x. In other words, it's the f prime of c dx. Okay. Sorry, I'm doing this during my office hours. Nobody's in there though, so nothing better to do. This is what I do when nobody's here. All right. So, anyways, it's this last relationship is kind of what I'm. Dy is equal to f prime of x dx. Okay. Okay, so one thing the book will have you do are comparisons between delta y and dy. So this used to be number 8. I'll just write it as an example now. Okay. So example, we have y is 6 minus 2x squared. We're interested in x equals -2, and our change in x, which is our differential of x, is 0.1. Okay, we want to compare delta y and dy. So delta y is going to be this thing above here, evaluated at x plus change in x. So it'll be 6 minus 2 times -2 plus 0.1 squared. And then minus, what do we have then? We have that thing evaluated just at x. So we'll have 6 minus 2 times -2 squared. Okay. Okay, so this thing then will become 6 minus 2 times -1.9 squared, and then minus 6 minus 2 times 4 is 8. So that'll be, if you plug it into your calculator, you'll get 0.78, okay, eventually. Okay, then we want to compare that to dy, the differential of y, which is just going to be f prime of, okay, so the differential of y then, let me think, it's f prime times dy. So f prime of x, in this case x is -2, and then times dx, which is 0.1. So we need the derivative. I guess I didn't get that yet. Up here under the EX, the derivative is -4x. Just up there somewhere. So this will be then -4 times -2 times 0.1, which of course negative times negative is positive. 8 times 0.1 is 0.8. You can see they're pretty close. So, oh great. Okay, so how about some maybe applications of these differentials? The first kind of application is in doing approximations. So for example, let's say you want to know the cube root of 27. The spiel is you do know the cube root of 20. So you want the cube root of 26, but you know the cube root of 27, and you could use that to figure out the cube root of 26. So the cube root of 27, of course, is just 3. So what you do is call this function f of x equal the cube root of x. And in order to pull this off, I'm going to need its derivative, so I'm just going to go ahead and get that. This will be x to the 1/3. Bring the 1/3 down, so you get 1/3 x to the negative 2/3. Right, so f of 26 you can reimagine as f of 27 plus -1. And what you're looking at right there is f of, kind of think of it as f of x plus change in x. Okay. And then from above, we know that, so let me write above here, we know what? We know f of x plus change in x minus f of x is our delta y. But we can approximate that with f prime of x dx, right? So in particular, we can solve for f of x plus change in x in this approximating equation and get f prime of x dx plus f of x. Okay? So with that in mind, then I'm going to rewrite this f of x plus change in x as f prime of x, which in this case is 27, times dx, which in this case is -1. So the 27 corresponds to x, and the -1 corresponds to the change in x. Okay. So f prime of 27 times dx, which is, we said, -1, and then plus f of x, which would be 27. Whoops, I wrote 25, it should be 27. Okay, so then we plug this material in, so I'll have 1 over 3 times 27 to the 2/3. I'm just plugging that into the derivative formula, if I rewrote it with a positive exponent, times -1, and then plus f of 27, which is the cube root of 27, of course, or 27 to the 1/3. And the magic of this, you could do all this in your head. All right, so you have -1 all over 3 times 27 to the 1/3 is 3, and then 3 squared is 9. So 27 to 2/3 is 9. And then plus 27 to the 1/3 is 3. Okay, so we'll get -1 all over, I guess, 27 plus, get a common denominator. So we get 81 all over 27, which equals 80 over 27, which is an approximation for the cube root of 26, believe it or not. You can go to your calculator and check it, but it is. Okay, it's really, really close. So that's one kind of neat trick you could pull off. Where is it probably used more, though? It's in applications when you're looking at error propagation. Okay? So you have a human in your workshop doing measurements, and whenever they do a measurement, they're not going to get the exact value. Okay? They'll get the exact value plus some sort of error. All right? Okay, so we'll use then this delta y to do this problem. So delta y again is f of x plus change in x minus f of x. Okay, and the x is the value that your workman is measuring. Okay, so this would be your measured value. So x plus change in x then is the actual value. like if you had a microscope, you can maybe figure that out, right? Actual value. And then the change in x is considered the measurement error. So this thing right here is your measurement error. Okay, and the delta y in this context will be considered propagated error. So this thing is the propagated error. Okay, so it's a little weird when you read the problem in the book. You're not quite sure as to what is the human measurement and what is the actual measurement. In the real world, you would know, but in these books, it's kind of a weird thing. Let me look at one of the problems just to make this clear. I'm going to find the actual page here for us. So the problem is about measuring a floor tile which is square. It says the measurement of the side of a square of a floor tile is 10 inches. Okay, so what is this 10 inches? This 10 inches thing is the measured value, the human measurement, believe it or not. Okay, so you have a floor tile which is square, and your guy from the shop goes and gets his calipers out and figures out that the sides are 10 each, 10 units, 10 inches, I guess. Okay, so in this context, x is equal to 10. That's the measured value. And then the actual value is going to be with this measurement error. So the measurement error, change in x, it says the measurement of the side of a square floor tile is 10 inches. Okay, so that's what your work person measured. Then it says with a possible error of 1/32 of an inch. Okay, that's your measurement error. And you're going to put plus or minus 1/32. Okay. Okay, use differentials to approximate the possible propagated error in computing the area of the square. Okay, so instead of figuring out delta y, we are using differentials. So that will be approximately dy, which is the propagated error. Okay, so the propagated error when computing the area of the square. Okay, so to compute the area, you're going x times x, in other words, x squared. So dy, we recall, is just f prime of x times dx. And in this problem, f prime of x, so yeah, our f of x is x squared, a prime then is 2x. So f prime of x will be 2x times dx. And we're given this information here, right? So we'll dump this information into this formula. Remember, little dx is the same as delta x. That's the differential of x. So we end up with 2 times 10 times plus or minus 1/32. Right? So at the end, you'll get 20 all over 32 as a decimal, though that will be... I'm looking at my notes, plus or minus 0.625, and we're talking about area, so this will be inches squared. Okay, well, we started with 10 inches on either side. Okay, so this is part A of the problem. Part B, they want to know about the percent error. Okay, so part B, percent error. To find the percent error, you find the relative error. Okay, so first we must find the relative error. To get the percent error, you just multiply it by 100%. Okay. Anyways, the relative error is going to be the derivative of our function. So in this case, I'll just go dA because that's an area function, but I'm talking about f of x. So if you wanted to, you could put df right there. dA with respect to a. Okay. So in the top we had 2x dx, and then the area formula itself we just said was x squared. Okay. And then we simplify this, we'll get 2 all over x times dx, and then for the relative error you just do substitution. Okay, so for this particular case, it'll be 2 all over 10 times plus or minus 1 over 32. As a decimal, that'll be plus or minus 0.00625, and that's your relative error. Okay, for the percent error then, all you're going to do is multiply that by 100%. So your percent error is plus or minus 0.625%. Okay. Okay, so not a big deal. Interesting stuff though. Okay, we will be mainly using the differential form of the derivative when we get to anti-differentiation, right? So we learned how to go in one direction with the differentiation. Eventually, we want to go in the other direction. Okay, so you know, if the derivative of sine is equal to cosine, the antiderivative of cosine must be sine. Okay, when we play around with those problems. The only problem is when you have chain rules, to reverse it, it gets really difficult. So we'll have to work with this differential form thingamajig. Okay, so this is, I guess, section 4 in my notes, the differential form. And so it's quite easy. Basically, from before, if you had y equals 2x, you knew the derivative with respect to x of y would be 2. The differential form just takes the dx from the denominator and kind of moves it to the other side. So you can imagine it as multiplying both sides by dx. Okay, but it's not really quite technically that, because the dy over dx represents a limit and all that jazz. But here, this would be the differential form of the derivative. So moving the dx over is just a way of thinking of it for the ease, for the sake of sanity. Okay. So another example, y equals 3x cubed. Of course, the derivative y prime would be 9x squared, but the differential form of the derivative would be dy equals 9x squared dx. Right? You just put the dx on the other side, and that would be your differential form. Okay, that's really it. Let's look at maybe one more, and then we'll call it quits for the day. So the example, y equals x tan x. Okay, we're going to need a product rule. So y prime is leave x alone, and then the derivative of tan is secant squared. Plus the derivative of x1 times leave tan x alone, and then tag on your dx. Okay, and there it is. Well, it should just be dy, right? Y prime would be dy over dx. So let me get rid of that. Okay, there it is. That would be the differential form of the derivative. Okay. Okay, so we'll leave it at that. As usual, thank you for watching, and we'll see you next time.